Welcome to the School of Batman, a podcast where we ask academics to help Batman fight crime using their research. I'm your host, Chris George, amateur scientist and professional Batman enthusiast. In today's episode, we have a very special one-off with Mark Lorch, editor and co-author of The Secret Science of Superheroes. Mark has a PhD in protein folding from the biochemistry department at the University of Bristol, and is currently a professor of chemistry and science communication in the Faculty of Science and Engineering at the University of Hull. Hi Mark, and thanks for joining us.
Hi there, it's a pleasure to be here.
Great, so a very exciting introduction. So you were the editor and co-author of The Secret Science of Superheroes. Can you tell us a little bit about that?
Yeah, so it's a book that's written by a whole load of fabulous scientists and science communicators from all over the country. So the idea of the book is that we needed to look at a particular character or something out of the movies or comics and ask the question, well, if the science in their world is the same as ours, what else must follow from what we see in the comic books?
Wonderful. So let's move on to some specific superhero concerns now. So normally what we do, we'd focus on a singular problem, and we'd be focusing on Batman and how you can help Batman. As you have such a range of experience, we thought we'd look into the wider DC universe and look at a number of different problems. And we'll look at the big guy himself, Superman. So Mark, if you were the boss of Superman, you're Superman's boss, how would you best apply Superman's very specific set of skills for the greatest good to all of humanity?
Well, this is interesting, isn't it? Because, Superman, he uses his powers, his super speed, his strength, etc., to fight crime. And the question is crime really the biggest problem that our society and our planet faces? And I think probably not. I think there are much bigger problems. The way that we generate our energy is pretty dirty. For example, we've got we use a huge amount of fossil fuels to transport material all over the planet. Maybe Superman should just be involved in global transport. I mean, he could lift up tankers, move them across the oceans in super fast speeds, reducing the need for us to burn a huge amount of fossil fuels. Or maybe actually there's something even better he could do. Maybe instead of even moving around, he could just be cranking a handle in a power station and generating clean energy that way.
I think that's a great application. Probably would make for a slightly less enjoyable and interesting comic book, but probably...
Well, there is that downside, isn't it? It doesn't really make for great reading, watching Superman cranking a handle in a power station. Yeah, less drama there.
Let's move on to a villain, and someone from the Batman Rogues Gallery. Let's look at Mr. Freeze. Mr. Freeze is a Batman villain who has to keep his body below sub-zero due to an accident. So he's a biological human who runs his body at sub-zero. Now that seems very fantastical, the idea of an animal running at that cold. But is it that fantastical?
Well, no. Actually, I think when we look at what exists in the biological world, that sort of gives us an idea about what, in a way, might be at least biologically possible. And there are organisms that live at sub-zero temperatures. There are fish in the polar seas that live in water that is below 0 degrees centigrade. Now, of course, the saline in the water, the salt keeps that water from freezing, but nevertheless, it's very, very cold water. But what stops then the fish freezing? And one of the things that they have adapted is these things called antifreeze proteins. So these are protein molecules that will bind to ice crystals. And as the ice crystals start to grow, they grow from particular points, and the ice crystals, these proteins, then bind to these points, these things we call nucleation sites, and stop the ice crystals getting any bigger. Now, the interesting thing with these fish is that if they then even touch a block of any piece of ice, they will freeze solid, because suddenly there's plenty of nucleation sites. Suddenly the ice that they've touched basically triggers a rapid freezing of the fish. So potentially all you need to do to beat Dr. Freeze is just throw a snowball at him. And he paradoxically, even though he is super cold, that should freeze him solid, assuming he uses antifreeze protein to keep himself liquid at sub-zero temperatures.
Margaret, and is that the same principle for how antifreeze on a car works, for example?
No, not at all. No, that's actually about more changing the structures of water slightly, and so that it doesn't, so that you lower the freezing temperature that way. But actually, you can see this rapid freezing technique happening because with quite a simple demo you can do at home, and that's where you can make super cooled water. So if you take a bottle of water and stick it in, so mineral water, and stick it in a bucket of ice with about a half a kilo of salt, the water gets to below freezing, but the water in the bottle won't freeze until you pick it out, give it a knock, and bubbles will then form in it, and those start to form places where the ice can start to form, and the bottle will freeze solid in a blink of an eye. So yeah, have look that one up. Super cooled water.
Wow, super cool indeed. So there's another villain that I think would be great to talk about, Dr. Polaris, who is a master of manipulating magnetic fields and manipulating any structure that kind of has iron and things like that in it. So that's a kind of power I think we can all understand. But is there anything else cool that maybe he might be able to do? Any other extensions of that power that haven't been explored?
I think his powers are somewhat underutilized. I think there's a lot more he could be doing with them, really. To understand what I mean here, you sort of have to think about what we know about magnets. So we're all familiar with magnetism in that, you've got a fridge magnet, it sticks to your fridge. Your fridge has got iron in it, and that's why it sticks. So that's a type of magnetism called ferromagnetism. But there's two other major types of magnetism. One is paramagnetism, and paramagnets don't have much of a magnetic field themselves, but are attracted to magnets. And an example of that is actually oxygen. And if you get some liquid oxygen, like I sometimes do, because that's the fun job I have, and you put a magnet near liquid oxygen, it will jump onto the magnet. And then there's another interesting type of magnetism called diamagnetism. And diamagnetism is where things are repelled by magnetic fields. So a really common example of that is hydrogen nuclei. So water is actually diamagnetic. Now the thing is, it's really weak, this interaction between a diamagnet and a magnetic field. So you don't normally see it happening in everyday life, this interaction of this phenomenon of water being repelled by a magnetic field. But it is there, and it's actually the basis of magnetic resonance imagers, MRI scanners. MRI scanners work on this principle of a magnetic field influencing the protons in your water in your body. Yeah, so there's another component to a MRI scanner. You've got the magnetic field, but you also have a radio transmitter, and that influences the nuclei as well and manipulates them. So if you combine a magnetic field and a radio transmitter, you can actually create, it's basically an MRI scanner. So all this supervillain would have to do is try to introduce some sort of radio transmitter into his kit, and he'd in effect have MRI vision. Yeah. So which was an interesting extra superpower.
I think it's probably time we move on to the last of our explorations today, and an area that is a bit more closer to home for your study. So we're going to look at Aquaman and a specific problem Aquaman might be having, which is for some reason he wakes up one day and he's having real difficulty in communicating with the wider ecosystem around him. He's not able to talk to fish or other animals, and communications channels are not coming back to him properly, and he's really confused about what's happening. He goes to Batman. He says, please help me out. I don't know what's going on.
Right, so one of the really key ways that organisms communicate in the oceans is via chemical signalling. So an organism might release a pheromone, for example, and its mate can then swim up that pheromone trail to find the mate. And their organisms also, obviously, they smell, or actually more accurately in the oceans, they taste these chemicals that might lead them to food or mates or places to actually settle, etc. as well. So chemical communication is really important in the oceans. Now, there's something else happening in our oceans of late, and the chemistry of our oceans is changing because carbon dioxide that we're producing from our emissions dissolves in the oceans, and as it dissolves in the oceans, it makes the oceans more acidic. As the oceans become more acidic, that then influences these chemical signaling molecules. So they can they will change shape, their charge will change, which means that then organisms it becomes more difficult for these organisms to sense those chemicals. Maybe that's what's happening here. You know, Aquaman's ecosystems, etc., they're becoming more acidic, and therefore the organisms can't detect these chemical signaling molecules and communicate via that mechanism as well. And actually, this is an area of research I'm involved in. We're looking at how these structures of these chemicals are changing in different pHs, and hopefully trying to get a grip of how organisms might react and be influenced by future ocean acidification.
So how does an ocean become more acidic? It seems like such a big thing to be affected in such a way.
I mean, it's really simple, actually. It's really, really basic chemistry. It's just that carbon dioxide, when it dissolves in water, it becomes carbonic acid, and that is more acidic. I mean, if you get some water and you blow through it, put a straw in the water, blow through that straw, the carbon dioxide that your body produces dissolves in the water and will make that water more acidic. So it's as simple as that. It's really quite basic chemistry.
Right, but I guess just with huge amounts of carbon dioxide being pumped out, that's the effect that it's having.
Yeah. So we're pumping out huge amounts of carbon dioxide, and in a way, our oceans have saved us from even worse climate change than we're already experiencing, because I think it's about a third of the carbon dioxide we emit ends up being dissolved in the ocean. And for a long time, people thought that was just a great boon, you know, because but then of course we realised that actually that's changing the chemistry of the oceans, and that's something that we're going to have to deal with as well.
So I'm guessing this is not part of a natural ebb and flow of pH levels changing in oceans throughout history. Have we got any evidence of that?
pH does change slowly, but nowhere near at the speeds that we're observing it. So we've seen a drop of 0.1 of a pH unit since the beginning of the Industrial Revolution. Now that doesn't sound like much, but the pH scale is logarithmic, so that's a really big change, per 0.1 of a pH unit. And that sort of changes, you know, would normally happen over hundreds of thousands of years. Now there have been in records examples of where oceans acidification has happened dramatically, not over these timescales, much longer timescales than we're dealing with now. But those have actually led to mass extinction. So this is where we've had massive volcanic eruptions, etc. And some of the mass extinctions have been partly attributed to changes in ocean acidification, the changes in ocean pH.
Right. So I think trying to address some of the wider issues as to how Batman might be able to help reduce that. Is probably out of scope for this podcast, but is there anything that he could recommend Aquaman might be able to do just to get some of those messages through in the short term as a smaller fix?
Well, one of the things that we've found actually with our research is that it's not all doom and gloom, because organisms still appear to be able to react to the chemicals, just not quite as well as they did before. So to get the same sort of responses, they've just got to produce more of the chemicals. So they've got to, just in chemical terms, shout louder. to get their voices heard. So that's the sorts of thing that maybe you can suggest there. They've just got to produce more of the chemical in question, and hopefully then the signal will still get through. In the longer term, well, we've got to decarbonise the economy and potentially come up with ways of actually maybe having carbon negative industry. So something that actually, as our economy grows, have things that actually remove carbon dioxide from the atmosphere. Or who knows, maybe there's geoengineering projects as well that Batman could invest in.
Wonderful. Some stuff for another day. That's all for now. Thanks for listening to this very special episode, and thanks to Mark for joining us.
Thanks very much. It's been a pleasure talking to you.
And you can follow Mark at Mark_Lorch, Lorch, on Twitter. And you can also read about the underpinning chemistry, physics and biology superheroes need to be superheroes in The Secret Science of Superheroes, available now from all good online bookstores. If you'd like to discuss your research on a future episode, email us at info@figshare.com.